When people say neural network, there's a tendency to think, oh, they are replicating a brain. And that's not really what we try to do with neural networks or artificial neural networks. If you have a completely, like a top-notch neural network, all the architecture is set up, but all of the weights are still random, then you're going to need millions of pictures.
What is convolutional networks?
A convolutional neural network is a specific type of network that is organized in a manner so that it looks at clumps of pixels that are close to each other. The thing about neural networks is that we as engineers know that they work, but we don't necessarily know why they work.
How do you actually do that? Do you sit in front of a computer with what resembles a MS-DOS screen? How is it actually done?
The first thing you do is you go capture data. On activities where you use AI for high-risk applications, you have to be able to explain it. And that's a big issue actually, because the best systems we have right now are not explainable.
What problems are still to be solved in your opinion? What are the most important problems?
It's going to be the same problems I mentioned last time. So it's going to be about
Hello and welcome to Big Ideas Only. Today we are once again diving down into computer vision, but now we are taking a more theoretical stance on it and trying to find out how does it actually work. And with us again, we have Andreas Møgelmose, who is, and in the former episode, I said the associate professor. There's more than one, but he's an associate professor of AI at Aalborg University, focusing on visual analysis and perception in that lab they have on that there. Andreas, welcome back.
Thank you. Thank you.
I think we ended off the talk in the last episode talking about, well, humanoids, talking about ethics in filming, all of this. But what we never really touched on was how is computer vision different from other types of AI?
It's not very different. It used to be that what we call AI now was divided into a lot of, you could say subfields, but in actuality completely different fields. So there would be some subset of researchers working on computer vision, trying to make computers see. They would use one set of methods that they had developed over the decades. People have been looking into this since the 60s. Then there would be other researchers looking into, can we make a computer understand sound? They would use their methods developed over the decades. There would be some people working on understanding language, understanding text, and they would have their methods. Over the last 10, 15 years, well, 10 since 2012 basically, these different subfields have all merged into one field that we call AI today, or that we call machine learning today, if we want to be more technical about it. And that's because it turned out that one of the breakthrough methods that applied to computer vision, which is called neural networks, and I'm sure we're going to talk about them more later on, these neural networks turned out to be very applicable in many other domains as well. So the breakthrough was in computer vision in 2012 at a particular competition we can talk about. And then the other fields they saw that conference with that competition, and then they said, well, that looks super promising. Maybe we can use that for our sound, or maybe we can use that for our text understanding.
That is so cool.
Yes.
So what you're telling me is that the entire AI revolution, which is mostly, I guess, in generative AI, large language models, these kinds of stuff, it all comes from a conference on computer vision.
Yes, basically, but it's not like it started in 2012.
No, I get that. Yeah.
In 2012, people built a super successful system using neural networks and a particular type of neural networks called convolutional neural networks. But neural networks had research way before. Like the initial steps for neural networks is something called Rosenblatt's perceptron, which was invented in the 50s, and then you had some nice theoretical properties of that made it look like maybe this is something, but then nobody could really make it work. And then in the 80s, a lot of people did lots of research in it as well, had a little bit of success, but not really. And then some other types of systems came in and were more successful during the 90s and the aughts. And then in 2012, there was somebody really cracked the code on neural networks in a way that was super profound, and that made all of these other fields take note.
You say it's called convolution. What's the word?
Convolutional neural networks.
Convolutional neural networks. It's a tongue twister. What is that?
We should back up and talk about neural networks in general.
Okay,
So
yeah.
when people say neural network, there's a tendency to think, oh, they are replicating a brain. And that's not really what we try to do with neural networks or artificial neural networks. But it is true that inside our brains, we have something called a neural network. Then we make something conceptually similar in the computer called an artificial neural network, or just also neural networks for short.
Yeah.
But it's not like we want to replicate exactly what happens in the brain. It's more along the lines of if I had been at a party with an uncle who was a neurologist and he had told me something about how the brain works, and then I'd had a couple of beers, and then I woke up the next morning and thought, I can probably build that in a computer, and then I would build it just based off of my memory of what he had told me.
Gotcha.
So what I'm saying is that it is certainly not a one-to-one mapping, but there are some similar concepts and some stuff that is connected in the same manner. So what we have in a neural network is a whole bunch of neurons. And these neurons can do simple math, like super simple math, fourth grade math. They can add stuff and they can multiply stuff. But if it turns out, if we have millions of these neurons and we connect them in the right way, then this can approximate basically any mathematical function. So the idea here is that if we can have some input
Hmm.
that is in the form of numbers. Sometimes it's a whole challenge to do that, but we can have some input that is in the form of numbers. Then we can run it through all of this math, and what comes out in the other end is basically a decision. And what's a decision? Well, it's also just a number. It's usually, in the simple case, a 1 or a 0. So imagine we have a picture of a cat, or a picture that we want to determine if it's a cat. That picture is numbers because a picture consists of pixels, and each pixel can be described by a single number if it's a grayscale picture. A single number just describes anything from darkness to completely bright pixel, anywhere from black to white. So we
Yeah.
can take this bunch of numbers, that is this image, we can run it through all of our math, and then we can get either a 0 or a 1 out at the end if our math is right, so to speak. So if we have really good math in this very complex system, then it will be able to give out the right answer from a given input. And that's a neural network.
Okay.
So an arrangement of relatively simple math that, if we have enough of it, can make these decisions.
And then the more
Then,
complex the decisions, the more complex the system, or the more
yes,
neurons or
yes.
nodes or whatever you call them
And
should be.
an important thing to understand is that there is so much math in here. There are so many parameters. So again, it's simple math, but there's a lot of it. So if we have millions and millions of neurons, then we also have millions and millions of numbers that are multiplied by other numbers.
Gotcha.
These numbers are called weights, and it's in these weights that the system holds its information. But there are so many numbers that I cannot tweak these weights by hand. I cannot look at it and say, oh, well, this weight should probably be 10. Nobody understands that. Nobody can understand that. So what we do instead is we use machine learning. So we basically show this neural network a huge number of images of cats and not cats. And then we also tell it if it's a cat or not.
Yeah.
So then we can show the picture, we can do all the math, and at first, all of the parameters in the system are completely random. And that also means that the output of the system is completely random. But then there's a system for adjusting all of the weights, so it adjusts more towards the right answer. So if we get a 1 and we expected a 0, we'll tell the system, oh, we expected a 0, and then all of these numbers will be adjusted a tiny, tiny bit. And that doesn't mean that it's then perfect, but it just does mean that we can show more examples, and for each example we show the system, it will adjust these weights a tiny little bit. And then if we do it enough times, and as you said, our architecture, so the structure of this network is good, then over time it will learn to make the right decision.
And how long time is that?
We usually measure it in sort of how many examples we need to show it, because time is relative here depending on how fast a computer you have. So of course, if you have a slow computer, it takes a long time. If you have a really fast computer, it goes fast.
Yeah.
If you have a completely, like a top-notch neural network all the architecture is set up, but all of the weights are still random, then you're going to need millions of pictures. So it's going to need to look at millions of pictures to sort of learn the sense of sight. But what we can then often do is we can leverage something that is pre-trained. So we can take a network that has been trained on a lot of examples first. That means that the weights are not random. The weights are actually adjusted towards some vision task. And then if I have another vision task, if I now need to detect fish or something else, then maybe this network is not good at detecting fish, but then I can get away with showing it way fewer examples of fish, because sort of the basic understanding of, well, if I am looking at things, I need to be able to look at color, and I need to be able to find edges, etc. That is already baked into the system, and we only need to fine tune it. We only need to fine tune it to be able to solve our specific task.
In my work, I just told you in the between the interviews here, I use a lot of large language models to create content to write with, basically. And when you do that, when you just scratch the surface of working with generative AI, people say you need to train your own stuff. People say you can fine tune stuff. Is that the difference? Training is like the whole thing from scratch, and fine tuning is,
Not
well,
entirely. Fine tuning is also training, but in fine tuning, we just don't adjust all of the weights at the same time. What we can usually do is so these neural networks are arranged in layers of neurons, and we can usually get away with only adjusting the last few layers if we're doing fine tuning.
okay.
What people often do in large language models, though, as users, is not training. What they do is they give the language models some more context. And that is a slightly different thing. So what large language models can do is they can guess words. So if you train a large language model, you take a lot of text, then you erase some random words, and then you ask it to replace those words. At first, with all of the random weights, it's very bad at that. But then we can do the backpropagation thing I talked about. I don't think I mentioned the word backpropagation, but then we can do the adjustment of the weights, and that's called backpropagation, until it is very good at guessing these words. And that's a large language model. A large language model is good at guessing words. So when we talk about generative AI, it's really just about stacking a bunch of decisions on top of each other. We no longer need to decide, is this a cat or not? We don't need to decide, is this tweet happy or sad? We need to decide what is the good next word in a sequence of words.
Yeah.
The way it can guess the next word is by looking at all of the previous words. And the previous words, of course, will have an impact on what is the next word. If it didn't, then it would just have random guesses, right? So it needs to take into account the previous words. In a large language model, we call that the context window. The context window is how many words it can look behind, so to speak. So if you have the context window of 2 words, for example, the model would very quickly lose track, because if I say my horse, then after maybe 5 words, it wouldn't know that it's writing about horses anymore, because how could it know? It can only see 2 words behind itself. So these large language models that are really large neural networks, they have a really long context window. ChatGPT can see 175,000 words behind. And what people then do to make them behave nicely is they add stuff into these 175,000 words. So basically, if I were to ask ChatGPT to write a text about me, it would probably just not be able to do it, because I don't think I'm trained into the system very much, because I'm not all that present on the internet. But so I would get something bad at least. But if I instead inserted a lot of information about me, like I found some newspaper articles maybe, and I found information about me, and then I asked to write a text, then I haven't trained the system. I've just added stuff into the context, and that has an impact on the probabilities of the words that it guesses, and then it makes better text.
Got you. Okay, let's try and come back to computer vision, and because there's a difference between generating stuff and then looking at stuff and deducting what it is and then reacting on that. Well, I asked, what is a convolutional network? And then you said we got to backtrack a little bit and talk about neural networks. So now we've done that. Then what is convolutional networks?
A convolutional neural network is a specific type of network that is organized in a manner so that it looks at clumps of pixels that are close to each other. So if we had just a normal neural network, which is called a fully connected neural network, then all pixels in the image can have an impact on all calculations in the network. In theory, this should work. In practice, it turns out we cannot train that properly. The system we have for adjusting all of these weights just is never able to make good adjustments so it can recognize the things we want it to be able
Why
to.
is that?
We don't really know.
I feel like that's the answer to many of those why questions.
Yes, yes. The thing about the neural networks is that we as engineers know that they work, but we don't necessarily know why they work. Um, it sort of goes back to the whole explainability point from last week. Um, so yeah, we don't know that, but it turns out it doesn't work very well. So what we can do instead is to say, okay, each little set of neurons only gets to look at a little part of the image. So you guys are responsible for looking at this part. You guys are responsible for looking at this part. You guys are responsible for looking at this part. We might also say that you guys define a way to look at a picture, and you can see a lot of small blocks in this picture with your parameters. And then another gang of neurons is responsible for looking at the picture in a different way. And then they can join forces, and then we can combine their understanding of the picture to get a better decision in the end. So it's a way we help the network by sort of directing it towards looking at pixels in a way that's helpful.
I'm not sure I completely understand that.
Without being able to draw, it is extremely difficult to explain a convolution. Gist of it is that a convolutional neural network looks only at small parts of the image one at a time, whereas a fully connected would look at the entire image at the same time.
And what makes it work then? Is that because you...
So what happens is that this neural network is arranged in a number of layers. And it turns out that the early layers learns simple stuff about the picture. So it learns to look at bright and dark areas. Then you can go a little bit deeper, and then you'll have layers that are really good at finding edges in the picture. Because it turns out if you want to detect something, you need to be able to find edges. Then you go deeper in the network. Then you'll have some layers that are good at combining these edges into maybe circles or triangles. Then in further layers, you will have some layers that are good at taking circles, combining them in the way that circles are arranged in our eyes, for example. So all of a sudden, many layers down, we now have parts of the network that is good at finding eyes. And then you might have, and mouths, of course, and other parts that can do these different parts of faces. And then you have another layer that is good at orchestrating these. So these eyes have to be arranged in a particular manner relative to each other so that we're looking at a face. And then in the end, it can combine the findings of these layers into where's the face in this picture. So it sort of builds up a gradual understanding of what is in the picture.
All right. And what sorts of challenges would the AI meet on the way?
Mm, So let me again back up a little bit and talk about what we did before these neural networks. So we had neural networks, the breakthrough in 2012 at this competition in recognizing images. Before that, we had what was called feature engineering. So feature engineering is not a particular approach, but it's more sort of a meta approach that in order to build system that understands pictures, then we have to define what is important to look at pictures. So back then, I as an engineer would say it's important to look at colors. If you want to be able to detect traffic signs, you need to look at colors. You also need to look at the edges, and you need to be able to combine these edges into shapes. And then I would tell the computer, you look at colors like this. These are the numbers you use. This is the way you can combine these numbers. This is how you find edges. This is how you can combine numbers from the image to find edges. This is how you combine edges into shapes. But I would not tell the system what colors or what shapes. It would have to learn that. And there are other ways that could be done via your neural network, but there are other methods for that as well. What happened in 2012, or at least, well, toward the late aughts, was that we realized we can't come up with any better ways of looking at colors or edges or combining edges. We had tried many, many things. We had some really strong systems actually, but we had sort of hit a ceiling. Then with deep learning, we say instead, I'm not going to tell you how to look at pictures because maybe you as a computer can find a better way for you to look at pictures. So the way we instruct computers to look at pictures early on was very biased by how we think it's good to look at pictures. Instead, we want to derive that from data. So now we just say that tell the system, here are millions of pictures instead of thousands of pictures, but now I don't help you very much. Maybe I help you by telling you what a convolutional neural network is, which is basically stuff that is close together is relevant together, but everything else you have to learn on yourself. And that's the big challenge in neural networks. How do you set up a learning regime and an architecture so the system can actually learn this from very many examples?
I always wonder, because I think in my head I somehow need a visual picture. How do you actually do that? Do you sit in front of a computer with what resembles a MS-DOS screen and write code, or how is it actually done?
There are multiple aspects to it. So the first thing you do is you go capture data. So if you want to train a system to detect traffic signs, as my earlier example, well, then you go out and you take 10,000 pictures of the same traffic sign in different scenarios. Now you have some data to base your work off of. Then the next thing you do is you program the system. So either you choose one of the old-fashioned ways, or you choose to use a neural network. And then for the neural network, what you program on code in your MS-DOS prompt, if you still use MS-DOS, most of us
That would
use
be
Linux.
amazing.
Yes. So most of us do work in a prompt still, but we do it on Linux instead.
Gotcha.
So then you would do programming to define the architecture of the network. So you would say there are this many neurons in this layer, there are this many neurons in this layer, they are connected in this manner. And then you have done that, then sort of an automated process happens. Then you say train, and then you basically have another piece of software, or you have your software run through all of these 10,000 examples, automatically adjust these weights using an algorithm called backpropagation. And then when it has done that for a period of time, you can sort of follow the graph of it's getting better and better and better. And at some point it just plateaus and can't learn more from your data. Then it's either because you have extracted everything you can from your data, or because your network is not capable of learning anymore. Then you stop it, and then you have a machine learning system that is done. Then of course you can plug that into an actual user interface.
I read a book on AI by a Swedish or Norwegian scientist called Inga Strömke, I think.
Mm-hmm.
Are you familiar with her?
No.
Okay, but she wrote like a popular science book on AI, and one of her examples was that they trained an AI on lots of, I think it was X-rays of something,
Mm-hmm.
and then in the data, it turns out that the machine got really good at recognizing what do I know, like broken bones, something like that,
I
and
think it was skin cancer. I think I know where you're
skin.
going.
Oh, really? Yeah. So, well, the idea was that instead of actually looking at the skin cancer, it would look at the frame of the image or something like
Yes.
that, or the
Yeah.
university stamp or something
Yeah.
like that.
There are different examples of this, but there's a very famous example about skin cancer where it turned out that they wanted to train a system to recognize a skin cancer. You'd have a mole or something on skin, and then it would be able to tell is this skin cancer or not. So it trained that on very many examples of skin cancer and of benign moles that are not dangerous. Turns
Yeah.
out that in all of the skin cancer pictures there was a ruler, because the doctor would like to show how
Oh,
big
yeah.
is this mole. Now, the ruler was not there for the negative examples because they were not really sick people. They had just taken some pictures. And it turned out that it was very, very good at this data. But then when they showed some real world data, it just didn't work. And that was because the system had learned to look for rulers, to
Yeah.
not to look for skin cancer. So that's why we need explainability. That's why we need the system to be able to somehow describe what it's looking at, what it's looking for, why it's making a certain decision. Otherwise, we can fall into this trap.
How do you avoid that? Because explainability is not just behind, it's not around the
No,
corner, is it?
no, we it depends. We have some systems that are totally explainable. They just don't work nearly as well as neural network systems do.
Okay.
So we have this trade-off that we can use some, I'm exaggerating here, but some really poor systems that are explainable, or some really good systems that are not explainable.
Mm-hmm.
And then what do we want? Well, sometimes performance is king. Sometimes we just want the damn self-driving car to not drive over the kid. So we would not, I mean, it would be a bad outcome if it drove over a kid and could explain why it did it, right? Rather than not drive over the kid and not explain why it did that. So
Yeah.
sometimes performance is king. In other cases, especially in healthcare, if you are told that you have cancer and you're going to die within 4 weeks, then you might be interested in knowing why they think that. So in that scenario, explainability is super, super important, and that's
Also,
also baked.
whether you're eligible for a bank loan
For
or something
example,
like that, those
so
kinds of
that's
stuff.
also baked into the AI Act that the European Union has just approved. So on activities where you use AI for high risk applications, you have to be able to explain it. And that's a big issue actually, because the best systems we have right now are not explainable.
I want to come into a little bit about how does computer vision interact with other kinds of systems? Because that to me seems quite obvious that that's necessary for computer vision to have any role in this world, not just towards like AGI or humanoids or all those kind of cool things, but also just industry recognizing whether it's a metal or whether it's a plastic.
So the most basic way a computer system would do something is it's a completely standalone system. So it's what we call a black box. There's a camera here, and then there's an output saying where is the trash. And that means that the output would simply be the coordinate in space, and then you can send that coordinate to the robot, then the robot would move and pick that thing up. So it can easily interact with all sorts of systems. Let me think of an analog, like if you have an old traditional car with a gearbox, how does the gearbox interface with the rest of the car? Well, the gearbox has an input, which is the engine that's spinning, and it has an output, which is the axle that goes to the wheels. What happens in the gearbox doesn't really matter. We just know that it transforms the speed of the engine to the speed of the wheels. Same thing for computer vision. The rest of the systems don't have to know how the computer vision stuff works. It can just be a completely separate module that does its thing, makes a decision, says here's the trash, or this is a dog, or whatever, and then the rest of the system can be a totally traditional software system or hardware system that can do something based on that information.
And would there be any instances where you would have to have systems interact more with each other? So say something feedbacking to
Yeah, we have
the computer
two
vision
two
system.
things that are really emerging. One thing is what's called ensemble models, and ensemble models is where we combine different specific AI systems. So you call it a specific AI or narrow AI if it can do only one thing. And all AI systems we have today are specific AI systems. We don't have general AI. So we have specific systems that are good for language. We have specific systems that are good for computer vision. We have specific systems that are good for robot control. But then you can combine these into an ensemble system. And usually you will have a large language model as sort of the orchestrator of this. So you have tried using an ensemble system if you have gone to Copilot or ChatGPT and asked it to make a picture. Turns out that ChatGPT cannot do this because ChatGPT is a language model, but it can recognize the language that is you telling the system to make a picture. Then it can activate another model called DALL-E in the case of ChatGPT, which is good at making pictures from text.
Well, not good, but
Well,
it can do it.
Yes, it can make some pictures. Then DALL-E will make this picture, it will send it back to ChatGPT, and ChatGPT will present it to you as if ChatGPT made this. But ChatGPT did not, in fact, make this. It just activated another system. So that's called an ensemble system.
Yeah, so that's also what's called multimodality.
Yes, but no.
Okay.
But that was my next point is we also have models that are truly multimodal in that they are not trained purely on text or purely on images, but they are trained on a mix of text and images. Becomes a little technical, but that means that information about a given topic along with visual information about what this thing looks like ends up in the same point in the knowledge space of these models. So in that instance, you have to have very tight integration between the different modalities.
That to me seems like a more valid way to go if you want to go to some AGI type of system, because to me it resembles how humans they understand the world better. I don't know, not necessarily that information about what a dog is, it's maybe not centered in one specific area of the brain per se, but the fact that I have input to draw from, that I know what a dog smells like, I know what it looks like, I know how it sounds, and all that kind of stuff.
Yeah.
It belongs together somehow, right?
Yes, and perhaps that is the way to AGI. Nobody knows because nobody has solved that
Well,
problem.
there you go. I just solved it.
Yes, very good. So now you go build it.
Oh,
So the thing is, we can do multimodality with text and images, for example. We can do it with text, images, and sound, perhaps. But the more modalities we add, the more complex the training is going to be. And if you want some sort of AGI, you probably also want some sort of physicality in there. So lots of people believe that you can't have AGI before you have actual agents, meaning robots that can navigate the world, because a lot of what we know as humans is not anchored in stuff that we have read or have been told or have seen. It's comes from sort of, as you also talk about, our sort of integrated experience of the world. Like from when we were a baby, we have learned what gravity is, and we know how things are going to act, not based on some formula or based on something we've been told, but just based on experience. And this is something that is really hard to capture in data and get into these systems.
Our time is now again literally up, but I want to ask you again, considering computer vision, the theoretical, the technical stuff behind making it work really well and making it work really well with other systems, what problems are still to be solved in your opinion? What are the most important problems?
It's going to be the same problems I mentioned last time. So it's going to be about making the models better at understanding things. Last time we talked about fine-grained classification, understanding the details, seeing the small things, making decisions based on that. It's going to be about explainability. Can these systems tell why they make a given decision? That's interesting from a technical point of view, but it's also interesting just from deployment, from the cancer example we talked about before. And it's also about how can we unlearn stuff from these things? How can we actually make sure that data can be removed from these things after they have been trained? Same list as in the last episode.
I just came to think about that when we look at stuff as humans, our focus shifts depending on what we look at. So I can look in this direction, but I can look at the lens, or I can look beyond the lens, and that kind of zoom out and zoom, and that blurs out obviously the rest.
Yes.
Would that be the case of computer vision as well? And
No,
if
generally not.
No, then would it be beneficial for systems to have that kind of feature?
No, because the systems do it in a different way. So the reason we do this with our eyes is basically a shortcoming of our optical system, or it's because our optical system needs to adapt to having different distances. So if you know anything about cameras, you'll know it's the aperture setting that controls whether stuff is in focus or not. And it turns out that if you tweak the aperture so that it is super, super small, then everything in frame will be in focus. And that is what we want for computer vision. That has some trade-offs. That means that your images get darker and you have to adjust other things for this to work. But really, in most computer vision contexts, we have a camera that has everything in focus at the same time. Because then at the algorithmic level, then the algorithm will learn what is important and what is in focus. So we don't need the mechanical adaptation that we do for our eyes.
But what happens in the software is then that it still kind of focuses in.
Yes.
All right. Okay. Well, that was a sidestep. I think our time is up. So thank you so much for joining, Andreas Møgelmose. And I hope to pick up this talk maybe in a year or so to see where we are, because at the pace we're walking right now with AI, or at least I don't. Has it slowed down a little bit? I feel like it has a little bit.
Yes, I think. I actually don't think it has been. Well, no, it's wrong to say that it hasn't gone fast. But the thing is, we have had a breakthrough in 2012 with the neural networks, and then a lot of stuff has happened that leads up to the 2022 ChatGPT breakthrough, which was not really like from one day to the other, but which has been also worked on since 2019 or more actually. So I think it's running sort of at the same pace. It's just that we've had a couple of milestones that were super, super impressive. And
just the fact that it became a public tool.
Exactly. So there's a Cassie Kuczynski, I think she's called. She used to be something like head of decision making at Google or some title like that. She's not at Google anymore, but she said that ChatGPT was actually mostly a UI revolution more than it was an AI revolution. Because it was about taking these models that programmers like me had access to and bringing them into a chat interface that everybody had access to. And that seemingly happened overnight. And I'm not trying to say that it's not important, and I'm not trying to say that there were no algorithmic improvements in ChatGPT. There are plenty, but I'm just saying that this is something that has happened over a long time, and also way back before 2012. It is going faster in the sense that more and more researchers are working on this, and that means that research output is enormous, and that means it's more and more difficult for somebody like me to keep up with the latest research. But I wouldn't necessarily, I mean, I know ChatGPT or OpenAI say that the next big model is going to come out this December. That's probably true. I don't expect a leap as big as when ChatGPT came out. Most normal people don't really understand or know that ChatGPT started out as GPT 3.5, and then 4.0 came out, and then 4.0 came out, and then 0.1 came out. And there are all of these different models, and they are all interesting, but to most people, they are all still just ChatGPT.
They're
There were
still the
no
same. Yeah.
huge breakthrough in any of these models.
Oh.
Again, lots of interesting stuff in them, but for the ordinary human being, no big deal. The next model that's going to come out from it is going to be the same.
You know what I think? I think that's very reassuring, because I think it's much more reassuring to know that the research kind of follows a fairly typical pace of research. Of course, it's dependent on how many people are looking at this problem. And the more
Yes.
popular a problem gets, the more funding it gets, and the more
Yeah.
people are looking at it. So, of course,
Yeah.
that's going to accelerate the stuff.
Yes.
But I think it's very reassuring that it's not accelerating at a pace that is, well, maybe it's unheard of, but it's not unnatural.
No, I don't think it is.
I think that's
That
very
yeah.
reassuring. Let's end on that, Andreas. Thank you so much for joining. And to you guys out there listening, thank you so much for joining as well. And if you like this episode, well, leave us a comment and share and like this episode. Of course, hit that subscribe button. You know what to do. And of course, if you have any questions, anything you want to ask me, anything that I can pass on to Andreas for you, hit me up at podcast@bigideasonly.com. And that was podcast@bigideasonly.com. And I look very much forward to hearing from you. I love hearing from you guys out there. I think that's it for now. Thank you so much for listening.